Okay, thank you, Marcy, and welcome everyone to today's session. Glad you are here, and must be a pretty popular topic. This is one of the larger events that participation rates that we've had, so this topic, I'm sure, is a big part of that. As Marcy mentioned, we're going to be talking about calculating wind loads on low-rise structures per the 2015 WFCM engineering provisions, and you see the accreditations there. You've seen the description and learning objectives, so we won't spend any more time with that. This is copyrighted material, and if you do want to use parts of this for something, you can write for permission from AWC to use copyrighted material. We are also an AIA provider, and you've seen that information as well. So Marcy mentioned poll questions, and here's our first one. Should be the easiest one, so we'll see who's in the audience with us today. And Marcy, I'm not hearing you. You might be muted.
Sorry, I was muted. What is your profession? Architect, engineer, code official, builder, or other? Fortunately, that was an easy one, and you could answer it without my reading it. All right, and as usual, I close these after about 80% or 30 seconds go by. So, and then I'm going to share the answers. We've got about 72% engineers, 17% code officials, 5% architects, and 6% others. So we are glad that all of you are here, and welcome.
That's great. Yes, welcome. And this, I'll go ahead and warn you, is a pretty heavy engineering topic. So the 72% of engineers here, we're hoping to maybe challenge you a little bit more today with some of the information that we're presenting. Let me just get my screen expanded a little bit so that you're able to follow along. And you've hopefully downloaded the PDF for today. We've excerpted from the wood frame construction manual and its accompanying commentary some provisions that are very specific to wind design. But one of the first things that you'll notice in the wood frame construction manual, and this is important because it's referenced in the International Building Code and the International Residential Code, but this table 1 at the very beginning of the document gives you a pretty good sense of whether you'll be able to use it to begin with for design. And we'll talk through some more limitations as we go, but one of the first things you'll see, and I'll grab one of my highlighting tools here, is that mean roof height is going to be 33 feet or less. Number of stories is 3 or less. And the building length and width must be 80 feet or less. And so if you're within those parameters for building size, then there's a pretty good chance you're going to be able to use the wood frame construction manual. The other issue that is important then is the loading conditions and or the loading assumptions. And so when we get down here to especially floor live loads of 30 to 40 pounds per square foot, that tends to limit the document to 1 and 2 family dwellings. However, what we'll talk about today is with the maps that we've developed and the buildings that you're looking at, if you just want to calculate wind loads on a 3-story structure and you're going to do the design yourself, you could still design or calculate wind loads on a 3-story structure. And even if it's a commercial building and you've got a 50, 60, or 100 pound per square foot load inside the building that might require you to do some other specific engineering, you can still use this document to calculate your wind loads. So want to make sure you understand that, and the wind loads are based on the ASCE 710 document. They're 700-year return, 3-second gust wind speeds, and we are going to show you how to get all three exposures shown here, exposure B, C, and D. So we know that in the residential code it kicks in at a certain wind speed of 130, and we'll talk about that here probably on this next slide, which is our wind speed map. So let me just rotate this map here on my screen. This is the only time I'm going to have to do this today, to rotate a page so that you can see it with me on the screen. So let me make sure I get it going the right way here. Sorry, let me just make sure I get the right page there. So bear with me just a second. Clockwise, 90 degrees, and that's going to allow us to talk about this map a little bit. So let me get rid of the toolbars, and this is a map from ASCE 7. Gives those wind speeds that we're talking about. This is for risk categories 1 and 2. And you see over here on the left-hand side of the screen, let me grab my highlighting tool again, pretty much all of the coast of Alaska greater than 130, which is this contour right here, is going to be required to use a document like this wood frame construction manual for residential applications. So that's a high wind region where that would be required. Let me bump up the size here a little bit on the map and take a look at some of the other regions. Again, I won't be jumping around this much for the rest of the presentation, but to get a good view of this map, it's probably helpful. Now, I think in the IRC, if I recall, they didn't shade in this region out here in the northeast coast. So I don't know that that's necessarily required by the IRC. There may be some special provisions within your own jurisdiction that would require that, but it is shaded. Again, once you get out beyond this 130 mile per hour contour, all along the mid-Atlantic coast here, North Carolina, South Carolina, I'm thinking almost all of Georgia, then down here in the central and southern part of Florida, you're going to be in that high wind region, then all here along the Gulf Coast here over through to Texas. So those are going to be areas, according to the IRC, where you get kicked out of the prescriptive provisions and have to use a document like the wood frame construction manual. So let's get this back to kind of a normal size again, and let me get that rotated back to where we can move on to the next slide. So those are, again, to kind of give you a sense of where that's required and where the IRC kicks in and requires some greater provisions. Now, we tabulate, as I mentioned, all the way down to 110 miles per hour. So even if you're not in one of those high wind regions where you need to go to another document, that is available to you, and you have the option to do that. And so these tools, as you'll see, probably are going to give you a little bit more conservative results in most cases than you'll get in the IRC. But if you need some engineering provisions, and we've talked about in previous webinars, if you want to use this for single-story non-residential structures that are in risk categories 1 and 2, like offices or restaurants, you can certainly use that. And then I believe even below that 130 mile per hour rate, range, excuse me, you'd need a document or an engineering basis like this. So this is section 2 of the wood frame construction manual. Gives you the enabling language, if you will, for this document. So the first thing I've highlighted there is that this information, this tabulated information, doesn't represent a complete engineering analysis, but is expected to result in significant time savings for the design professional. And so that's one of the things we want to show you here, and I want to express appreciation to those of you who provide feedback on the surveys, because this particular webinar is a direct result of comments and feedback from those surveys that we've received. And what we want you to go away with here today is an understanding of what's incorporated here that will hopefully be a significant time-saving tool for you as a design professional and as a code official who may be doing plan review. This should give you some tools to help you in your job as well. So we'll talk about load path and continuous load path to transfer all lateral and vertical loads from the roof, wall, and floor system down to the foundation. And so that will be part of our discussion today. Anything not complying with this section, I'm here in 2.1.3, shall be designed in accordance with accepted engineering practice. And so that's where it kicks you into the National Design Specification for Wood Construction, the Wind and Seismic Standards. So you can mix and match prescriptive provisions with engineered provisions. And so if if 90% of your building you can design with the prescriptive provisions, but you've got some concentrated loads, some sunroom or something that just needs some extra attention, doesn't meet the shear wall aspect ratios, those can certainly be designed onto the prescriptive provisions that we'll be talking about here. But I wanted to point out here in 2.1.3.1, this is the adjustment for wind exposure and mean roof height, because this is going to come up over and over again as we go through the presentation today. The highlighted section for buildings cited in exposure categories C or D, wind-related tabulated values shall be increased in accordance with the adjustments that are shown here in this table. So I'm going to jump back up here to this table, 2.1.3.1, over here on the top right of this page. And you see this is adjustment for wind exposure and mean roof height. So we're going to tabulate based on exposure B, and then if you have different mean roof heights, either that range from 0 to 33 feet, that's one adjustment you can use. And then you can also adjust for different exposure categories, C, and we're going to provide factors for exposure D. So when we calculate lateral and uplift loads here in the tables that you see during this webinar, these are the coefficients you can use to adjust for mean roof height and for different exposure categories. So that's an important table you want to mark in your book and be aware of the information that's there. So I'm going to jump then to the next page, which is page 35. It's the page number at the top in the black bar there. I kind of lost my page numbers here on the PDF, so when I got rid of the menu, but it's figure 2.2a, and this graphically shows some of the typical lateral framing connections that we're going to be looking at in the document. Now, as you look at these drawings, you see, it's a lot of nails shown here. We will show a couple of steel straps. We know that there's connection hardware out there from different connection manufacturers available. And so one of the things you'll also see in this document for connection design is where we'll tabulate loads at these various locations. Then you can pull whatever connector you need right out of the connector manufacturer catalog. But in Chapter 3 of the Wood Frame Construction Manual, we're going to show solutions for nails and generic straps as well to handle the loads that we're going to calculate here in Chapter 2. So again, graphically, this is just showing load path, where we're going to be focusing in on some of the lateral and uplift connectors. On page 36, these are the shear connector locations, and so we're going to be looking at roof to wall shear connections, wall to floor shear connections, floor to wall going down through the structure, and then eventually floor to foundation shear connections. And so those are all tabulated, and again, then when you get to Chapter 3, you can actually use some of those tabulated loads to size nails or straps or other connection devices. We'll talk about wind uplift connections as well, and so when we do that, we're typically talking about straps, although one of the newer provisions in the 2012 and 2015 Wood Frame Construction Manual is the allowance to carry uplift through the wood structural panels and get rid of some of these straps, these steel straps, but that uplift load also affects the anchor bolts here that you see down at the bottom of the wall system, floor system as well. All right, so on to page 38 and figure 2.2D, and this is an overturning detail, and the reason I want to spend a little bit of time talking about this is because of a simplifying assumption that we make in the Wood Frame Construction Manual that you need to be aware of. So I'm going to scroll on down to some of the equations here and talk to you a little bit about that tension end overturning restraint. And here's a note right here on the left that says that it can be provided by dead loads, perpendicular walls, or mechanical anchorage in accordance with section 2.2.4. So as a designer, you certainly have the judgment to take into account those any dead loads or other resistance from the building that you know is there. On the compression end, that's going to be resisted by stud end bearing on the plate, and so we've got to make sure we've got enough end bearing for that. But here's what I want to point out, and that is that the overturning loads, the required hold down capacity T, is based on the unit shear capacity of the panel, that first panel here in the wall. So I'm going to jump back up here to the drawing so you can see what I'm talking about. This first, typically a 4-foot panel or whatever is meeting the shear wall aspect ratio in that corner is going to have a certain capacity. Let's say it's 335, 336 pounds per linear foot. We're assuming that that panel is going to pick up 100% of the load, or of its capacity, and use that to calculate this hold down force. And again, that's a simplifying assumption for the Wood Frame Construction Manual. It makes it really easy for us to tabulate values. We know that engineers use different assumptions for that, and will spread the load out along the wall and perhaps take determine that hold down based on the actual load and how it's distributed. But for purposes of the Wood Frame Construction Manual, it's based on 100% of the capacity of that first panel. And so just know going in that that's the way we tabulate capacities and hold down capacities and the assumptions that we make in this document. Again, as an engineer, you're able to make other simplifying or other assumptions based on your judgment. So that gets us through a few slides there, and I'm going to ask Marcy to come back and help us out with our first poll question. Again, this is to kind of engage you. It does not affect your CEU, but let's just see how you're doing with the material.
Perfect. All right, so adjustment of tabulated wind values for buildings is based on which of the following? Is that exposure category, velocity pressure, mean roof height, all of the above, or answers A and C? So answers A and C are exposure category and mean roof height. So, all right, I've got about 60% voted, so I'd like to get that up to 80. And you're about there. So I'm going to go ahead and close and share. All right, so about 68% of you said both A and C, so exposure category and mean roof height. About 27% said all of the above. 3% said exposure category, 2% said mean roof, and nobody said velocity pressure. So, Buddy, what is the real answer?
All right, so very good. 68% of you got that right. The answer is E, A, and C. So it's based on exposure category and mean roof height. And let me just jump back up to that table real quick. Sorry for the slides flying by you, but I want to get there. Table 2.1.3.1 is table we looked at earlier, and this is the adjustment for wind exposure and mean roof height. And so the velocity pressure really doesn't enter into consideration here for this one. So let's keep on going then. Let me jump back down here past the poll question and see what we've got in the way of commentary. So this, again, the wood frame construction manual comes in two parts. The main document we just looked at, and then we've got a commentary that comes packaged with the document. And so one of the first things you'll see in the document here in C111 is scoping the applicability limits of this document. And the second sentence there, this limitation is related primarily to assumed design loads and structural configurations. Code prescribed floor design loads for dwellings generally fall in the range of 30 to 40 PSF. So we kind of harp on this over and over and over again, but it's just so you know where this can be used and how it might help you in the design process. The document, if you fall within residential construction and all the limits that are imposed, can be used pretty much anywhere for residential applications. What we try and distinguish is the floor live loads of 30 pounds and 40 pounds per square foot, where you probably wouldn't be able to use it for multi-story non-residential applications where the floor loads might be 50 or 60, 100 pounds per square foot. But again, if you're just designing the wind loads on the exterior of the structure, then designing a 3-story office building, for example, if you want to get the wind loads on a 3-story office building and it falls inside of these parameters, then this document is perfectly useful at that point. The building really doesn't know whether it's an office building or a residential structure in terms of wind loads hitting the building. So that's, again, something we want to make sure that you understand and are aware of. The design loads all come from ASCE 7-10, and so point that out as well. Here under this section at the bottom left of this page talks about wind loads, and that the wind forces are calculated assuming a box-like structure with wind loads acting perpendicular to the wall and roof surfaces. Lateral loads flow into the roof and floor diaphragms are transferred to the foundation via shear walls. Roof uplift forces are transferred to the foundation by direct tension through the wall framing and tension straps. Shear wall overturning forces are resisted by the structure dead load and supplemental hold down connections. So again, just when we talk about load path, This is a little primer here on some of the assumptions that we're making with regard to load path. Excuse me just one second. I need to attend to something here. All right, so I'm hoping you can still hear me, and I had to adjust a volume setting there for just 1 second. Let me just make sure I'm going back up to the top of this page. And making sure that my audio is still working. Okay, we're good. So top right of this page, and let me again get rid of some toolbars here to make it a little easier to see. Buildings are assumed to be enclosed structures in which the structural elements are protected from the weather. And we talked about the 700-year return, 3-second gust wind speeds corresponding to an approximate 7% probability of exceedance in 50 years. So that's all from ASCE 710. And again, we tabulate for 110 to 195 miles per hour. So the basic design equations then here on the right include both main wind force resisting system and component and cladding wind loads. And so the main wind force resisting system procedure shown here, abbreviated MWFRS, and you see the coefficients and the calculations that are used. You see the ASCE 7 section numbers for these equations and the figures that are used to get the coefficients. So that's the background that you need as we're working through these examples for CNC pressures, and we'll talk about where those apply. Again, here's where we're getting those from ASCE 7 and the figures that we're using to calculate or to determine those external and internal pressure coefficients. So we've actually shown a calculation of some various ASD velocity pressures for various wind speeds shown in table C 1.1 at the top of page 3 here, which is the next page in the document shown up on your screen. So this is for exposures B, C, and D at a 33-foot mean roof height. So the equation we looked at just a second ago, it shows up right here. There's some coefficients there. The K sub Z factor is the velocity pressure exposure coefficient. We assume that to be 0.72 from ASCE 7. For K sub ZT, that's the topographic effects factor. We assume that to be 1. And then the K sub D is the wind directionality factor, assumed to be 0.85. And so these are, again, some of the assumptions that we're using to develop this criteria. Here's a calculation where we're going to look at calculate an ASD velocity pressure at 150 miles per hour in exposure B. And so using the coefficients that we just talked about, we come up with 21.15 pounds per square foot. So up here in the table at the top of the page, you see how that's tabulated. So that's a similar approach that you could use to come up with any of these velocity pressures that then are used in the design process. We've done a lot of that work for you here. Let me just see if there's anything else here. Oh, let me talk a little bit about table C 1.2, which is the wind speed conversion table. This also shows up in the International Residential Code, but it gives you the transition from ASCE 705 basic wind speeds to the equivalent ASCE 7 basic, ASCE 710 basic wind speeds. And so in the IRC, they're still showing their basic wind speeds as based on that older standard, ASCE 705. So if you're looking there and then trying to use our wood frame construction manual, you've got to be able to do that conversion. And so when they talk about 100 miles per hour in the IRC, that's 130 in the wood frame construction manual. So I believe the IRC in some of the like the 2012 edition, I'm not sure if it's in the 2015, have those triggers at 100 miles per hour. That's 130 basically in the wood frame construction manual. So just be aware of that. There's some additional commentary here that explains that just below the table. Next, let's talk a little bit about internal pressurization that's used in the design. Internal pressure and internal suction for main wind force resisting systems are outlined in the couple of tables that follow. And so we're going to use the worst case of those pressures in our design. So we'll look at those tables here in a second, but I just want to point that out to you when we get to those tables so you know kind of what we're talking about. Let's talk a little bit about shear calculations. So we showed some diagrams earlier that talked about shear calculations. I just want to give you a sense of, again, we're working from the commentary here. Some of the back, what's highlighted here is third paragraph under shear calculations, talks about lateral roof and wall pressures for determining diaphragm and shear wall loads are calculated using main wind force coefficients. So shear walls and diaphragms are going to use main wind force. Spatially averaged CNC coefficients are used to determine lateral framing loads, suction pressures on wall and roof sheathing, and exterior stud capacities. And we'll spend some time talking about stud design a little bit later on in the presentation. For uplift calculations, for roof cladding, it's calculated using CNC loads. And uplift connections for the roof framing members then are calculated using enveloped main wind force loads. So the cladding uses CNC, the uplift connections for the framing members use main wind force loads. So just be aware of that difference. The uplift load minus 60% of roof or ceiling dead load is applied at the top of the uppermost wall. And as this load is carried down the wall dead load is included in the analysis. So those are some of the dead loads that we're going to use to offset uplift loads. 60% of the roof ceiling dead load, and then wall dead load. And I believe we're going to use 60% of the wall dead load as well to offset uplift. Then when we get to overturning calcs, in the wood frame construction manual, overturning loads are differentiated from uplift loads. So we just talked about uplift in the previous section here just above. That's direct wind uplift, and we make a very clear distinction, and you need to hear me say this, that when we talk about overturning loads, we don't use the term uplift typically. We're going to talk about overturning loads or hold down restraints to distinguish that from uplift loads, which are going to be anchor bolts and straps and things like that to handle true uplift from wind loads acting across the roof of the structure. So the overturning moment results from lateral loads that resisted by the shear walls. And we talked about our assumption for hold downs, but the uplift forces arise solely from uplift on the roof, and those go into the walls, and eventually down into the foundations. All right, we're not going to spend any time talking about gravity loads in this particular webinar. Over here at the bottom right, section C 1.1.5, protection of openings. Wind pressure calculations assume that buildings are fully enclosed and that the building envelope is not breached. Penetration of openings, such as windows and doors due to flying debris, can occur in sites due to high winds with significant debris field, and where this occurs, opening protection, special glazing may be required by the local authority to ensure the building envelope is maintained. So we are assuming in the wood frame construction manual a fully enclosed building with no breaches in the envelope. So that's important to know. I mentioned the internal pressures earlier that we assume. And so here's the first table that tabulates those internal pressures. Here's an example of 150 mile per hour, 33-foot mean roof height, exposure B, calculation of those internal pressures. So I'm going to keep going down through here. We know those are different for different zones in the building, and we're going to talk about these different zones and how the wind loads are higher at the edges of the roof and wall zones. We also deal with internal suction loads, and so this table, C1.3b, calculates an example of internal suction loads at 150 miles per hour and exposure B. And so we're going to use those worst case scenarios as we're developing wind load pressures in the wood frame construction manual. So again, we're digesting a lot of information. Let's just see how we're doing with that, and I'll ask Marcy to come back and help us with the next poll.
Yes, indeed. Sorry about that. Give me 1 second. I lost my screen. There we go. All right. So main wind force resisting system, MWFRS loads are used for which of the following? Diaphragms, shear walls, roof framing uplift connectors, all of the above, answers A and B only. Which of those would it be? I love how everybody's right on top of it and they start voting right away. All right, I've got 70% voted, so just a little bit more. And there's a clear answer that is not right, apparently, because nobody's voting for it. Can't fool them. All right.
We have some very sharp attendees.
We absolutely do. All right, I'm going to go ahead and close and share. All right, so hopefully, and I'm sure that it's not, diaphragms. Nobody voted for diaphragms. But 53% say all of the above, 40% say answers A and B only, and 5% say roof framing uplift connectors, 2% say shear walls. Buddy, the real answer is?
Okay, 53% of you got it right. It is all of the above, and I tried to make a point earlier when we were talking about the roof suction loads are going to be determined based on component and cladding, but the roof framing uplift connectors are per main wind force loads. And so we'll look at that as we get a little further along into the webinar, but many of you, more than half of you, picked that up along the way, so congratulations. All right, so let's jump now to our list of tables here on page 61. I'm sorry I don't have the PDF page number, but if you're following along on the screen, what I did for this particular webinar was just selected the tables from Chapter 2 that deal with wind loads. So we tried to break this out into two different parts that'll make it a little easier for us to teach this month and next month. So this month we're going to look at wind loads only. Next month we're going to look at gravity loads. So the ones that are highlighted here are the wind load tables, and so this sort of forms the outline for what comes next. So I won't go through each of these highlighted table names, but just know that this is what's going to follow as we go on through the program. So we'll start here with table 2.1, which are lateral framing connection loads from wind, and this is from the main document, the wood frame construction manual. And let me scroll down a little bit so we can kind of get the meat of the table here in front of us. Actually, let me jump down here first and take a look at the picture. If you have the PDF in front of you, you already see the picture, but for those of you who may not have the PDF, let's look at the lateral framing loads that we're talking about. So here, where this arrow, these arrows on the left point to lateral framing loads is really what we're looking at calculating here. It's where, with the load on the wall, creates shear in this plane between the top plate and the floor system. So we're going to calculate loads at those locations. So back up here to wind speed, and the reason I highlighted this one under 150 will become a little bit clearer to you here in just a second, but remember that number 148 for a 10-foot wall height and 150 mile per hour wind load. Notice footnote 1 says that tabulated framing loads are permitted to be multiplied by 0.92 for framing not located within 3 feet of the corners if the building is less than 30 feet, or W over 10 of the corners for buildings greater than 30 feet. And this is getting into a little bit more specific detail in the ASCE 7 standard, wind load standard, where again we know that there are higher wind loads at the edges, the corners of the building than there are in those interior locations. So what we've done in this case is we've tabulated the worst case. We've tabulated basically those end zones, those corner zones of the wall, and we're saying you could take an 8% reduction to those loads for the interior portions of the building. However, I think from a practical standpoint, if you're going to be sizing connectors along a wall, you're probably going to size for that worst case load scenario. So this probably makes the most sense, but just know that that's why that footnote's there, and we'll show you how we calculated that in a second as well. The tabulated framing loads also assume exposure B, which we talked about earlier, so now I'm looking at footnote 2, and a mean roof height of 33 feet. So if you're in exposure C or exposure D, you can go back to that table we looked at earlier and multiply by those adjustment factors for exposure C and exposure D and different mean roof heights. So if you had a single-story building, for example, maybe a 15-foot mean roof height, in exposure C, you could go in and use the adjustment factors there to calculate your loads for that particular building based on what's tabulated here. Now the other thing you need to be very careful about are these footnotes, like footnote 3 that show up here, that say that the tabulated framing loads are in pounds per linear foot of wall. And so if you have something other than a 12-inch on-center spacing, then these are your adjustment factors to get to those other spacings. So typically going to have to multiply by a 1.33 factor to get to your 16-inch on-center capacity that you need. Footnote 4 talks about headers, girders, and window sills, and that can be multiplied by 0.5 or half of the span to come up with your load for the end of those members. So there's a very simple way for you to tabulate your loads at the end of headers, girders, and window sill plates as well. So now what we have next on page 13 of the commentary. So notice up here at the top of the black bar, it's the commentary, page 13. What I've done is I've excerpted from the commentary of the wood frame construction manual the solution to what we highlighted earlier in the table. So in each of the tables of the wood frame construction manual, what we've done in this commentary is given you a solution to one of those cells. And this shows you where we got our wind, how we calculate our wind pressures, whether we're using main wind force or components and cladding, and how we came up with that result. So as a designer, you can get a comfort level with the assumptions that we've made, and whether you want to make those same assumptions and use the tables that we've developed in this document. So the procedure shown here in this paragraph is to use external or end zone components and cladding pressure coefficients and internal pressure coefficients for an enclosed building. So jump down here to the background. The CNC coefficients give us a higher wind load relative to main wind force. And for long, narrow tributary areas, the part that's highlighted here, the area width may be increased to 1/3 the framing member span to account for actual load distributions, which results in lower average wind pressures. The increase applies only to calculation of wind force coefficients. So again, we're trying to give you a sense of the assumptions we're making. Note, again, we're going to calculate this example assuming a 16-inch on center connection spacing, 150 miles per hour. You see some of the other assumptions shown here. The minimum, so the stud tributary area, sorry, let me try and highlight that for you, is 13.3 square feet, but the minimum required for analysis is h squared over 3, which is 33.3 square feet. So then we're going to come up with the appropriate coefficients. Sorry, let me scroll back up to the top of the page, get back up here. We run through those, and so we can get through all these tables. I can't spend a lot of time just to give you a sense of what we've done. Multiply by half the stud height for that tributary area to determine the unit lateral framing connection load, 148 pounds per linear foot. Which is what we tabulated above in the wood frame construction manual. But again, if you're at 16 inches on center, multiply that by that 1.33 factor to come up with your value that you need in design. And that's what shows up in footnote 3 above that we talked about a little bit earlier. So we also talked about those end zone and interior zone calculations. So here's under footnote 1 how we calculate that 0.92 coefficient. So we're going to take the end zone and interior zone coefficients and take a ratio of that, zone 4 to zone 5, to come up with that 0.92 factor that we showed up there in footnote 1. So again, check. This gives you a sense of how we make those assumptions and how those are tabulated for you. So now we can jump to uplift connections, table 2.2a. We're back in the wood frame construction manual. So you see how it's tabulated for 110 to 195 mile per hour wind speeds. Over here on the left, and these are for roof-to-wall, wall-to-wall, and wall-to-foundation connections, so these serve multiple purposes. We tabulate a design dead load of 0 to allow for, one, for you to calculate loads in exposures C and D. So if you're going to use that table, this table to calculate for different mean roof heights and different exposure categories, you're going to want to use this top row here before you go on and make additional adjustments. But then we've got different roof ceiling assembly design dead loads and different roof spans. So note this value here in the middle, out from 15 pounds per square foot under 150 is 326 pounds per linear foot. That's the one we're going to solve in just a second down here in the commentary. So just remember that number. Again, tabulated loads not within 6 feet of the corners for buildings less than 30 feet, or W over 5 for buildings greater than 30 feet. Get this 0.75 adjustment. Again, we know the end zone loads are higher, so that's how we tabulate, and you can reduce those for those interior zones. Mentioned this a second ago. Tabulated values for 0 are multiplied by the appropriate adjustment factors from table 2.1.3.1 for different exposure categories and mean roof heights. Look at footnote 4. Total uplift minus 0.6 of the roof ceiling assembly design dead load. So we've already accounted for 0.6 of that roof ceiling assembly. That's why we show those roof dead loads, roof ceiling assembly dead loads in the table itself. Take a look at footnote 5. So this is tabulated for roof to wall. If you're going to calculate wall to wall or wall to foundation, then you're going to want to reduce each of those by 73 pounds per linear foot, which is basically 60% of the assumed dead load of the wall above. So again, know how this table works with some of the assumptions that we make here, and it will really help you in the design process all the way down through to the foundation. There's some other footnotes down at the bottom there for headers and girders, and we've talked about some of those already, so I'm not going to spend a lot of time with those other footnotes. So I'm going to jump back to the commentary to table 2.2a. We're going to use main wind force resisting system loads for uplift connections for the roof to wall. And again, that was one of the poll questions we had earlier. The worst case, but look under background, the worst case uplift loads occur at a 20-degree roof slope with wind perpendicular to ridge and roof overhang uplift forces included. Okay, so the worst case occurs at a 20-degree roof slope. So be aware of that. For this example, you can see what's given here, and I pointed to that cell in the table earlier. These assumptions are used to calculate this one cell in the table. We then talk about where we get our pressure coefficients from ASCE 710. We're going to take pressure coefficients for the bottom surface of the windward overhang and use a gust factor of 0.85 and a pressure coefficient of 0.7. So we are assuming a 2-foot overhang. Might have glossed over that in the when I highlighted this a little earlier. We're using positive internal pressure coefficients to the bottom surface of the leeward overhang to model background pressure. So be aware of that. And so you're getting a sense, I know if you've already tried to use ASCE 7, of how complicated and difficult it can be. So I hope you're getting a sense as we work through these examples that we've done a lot of background work, a lot of the calculations already. So dead loads resist uplift forces, and so we're going to multiply those by 0.6. We're going to sum moments about the leeward roof to wall intersection. The uplift forces are calculated for a 1-foot wide section through the building. So I'm at the top right now, showing you where we're summing moments about the structure. We'll take a look at a diagram here in a second. We're going to add the dead load of the roof. That's already been multiplied by the 0.6 factor. And we'll sum moments about the leeward top of the wall. And that comes up with this value of 326 pounds per linear foot, which we talked about and pointed to earlier from that table in the wood frame construction manual. And again, if you're at 16 inches on center, which is pretty common, you're going to have to multiply that by 1.33. Footnote 1 talks about those end zone pressures. So I'm now moving to the next page, 15 of the commentary. And so if we compare that end zone uplift force to the interior zone uplift force, we come up with that factor of 0.75. So that's, again, allows you to distinguish between those end zones and interior zones. And here's just a graphic that shows how we're, what kind of loads we're assuming, including dead loads, the uplift forces, including the uplift loads on the overhangs and how those are going to be a little bit higher, and how we've summed moments about that leeward wall to come up with those uplift loads, F sub W, that was shown above in those calculations. So hopefully that all makes sense, and again gives you a sense of how useful this document can be. We'll move on into ridge connection loads now, and this is table 2.2b of the wood frame construction manual. Let's see, we're highlighting here again, we typically are going to base it on 150 mile per hour wind speed, and these are going to be based on roof pitch. So we show roof pitch over here on the left, and we're going to tabulate that unit connection load, and this is to give you a value for either a ridge strap or a collar tie. So let me just stop here for a second and talk briefly about collar ties versus rafter ties. We do this often, but it's often confused out there. The collar tie, if you're using one in your building, is used to connect the ridge together to resist the loads that we're showing here in this table. So that load is based on uplift. It's based on suction on the roof, and we're trying to prevent the roof from opening up. So those collar ties have to be on every rafter. You can't go every other rafter, which is common practice in some areas, and resist those loads. We're calculating this based on loads at every rafter. So collar ties at every rafter, or ridge straps at each rafter location. Those ridge straps typically would go across the top of the roof sheathing, just for to make it easier to install those, and then the shingles go across the top of the plywood and those ridge straps at the ridge of the building. So these are those connectors that are the connection loads that are used to calculate those. And the collar tie is different from a rafter tie, and in that the collar tie resists those uplift loads. The rafter tie resists thrust loads at the top plate or along the bottom of the rafter, and we'll be talking about those next week in the gravity, next month in the gravity webinar that we're going to be doing for this. So we're at 150 miles per hour, and this is the value 336 here. We're going to calculate for 712 to 1212 roof pitch. Again, look at footnote 1. We've got that 0.7 factor for framing not located within 6 feet of the corners, or W over 5 if it's greater than 30 feet. And so interior and end zones are accounted for with this 30% adjustment factor here. I've already talked about footnotes 2 and 3 multiple times. We've talked about footnote 4 with dead loads already. Here's a new one in footnote 5. So, and I've made myself a note here to make sure that I cover this in the discussion. For roof joists, so it says for buildings with roof slopes less than 3 and 12, the roof framing members shall be attached to the ridge beam with connectors in accordance with table 2.2a. So why do we do that? Why do we say that? The note here, and I don't know if you can read it on your screen, so I'll share it with you. But again, it was to make sure that I remember to share this with you all. A roof joist less than 3 and 12 supported by a ridge beam is assumed to be one slope, and so it uses components and cladding loads. So we're going to see in a second that we're using main wind force loads here, I believe. But if you're less than 3 and 12, we're assuming a ridge beam, and a single slope or a uniform slope, so that's going to use component and cladding loads, and so that's going to give results that are comparable to table 2.2a, even though it's 2 times the moment arm. And I really I spent a lot of time when I was preparing for this webinar studying this part, so you just have to take my word for it. When you look at this moment arm in a second and you look at what we're doing here, just know that for those low slope applications, we've created a simplifying assumption that is conservative. Okay, so I mentioned main wind force loads, and so that's what we're going to use to calculate these ridge loads, these ridge strap or collar tie connectors. Here are our assumptions under the example here. 150 miles per hour exposure B, 33-foot mean roof height, 7 and 12 roof pitch, 36-foot roof span, and then some dead loads shown there. So let me jump down here to the picture, show you the diagram, which will probably help you know kind of how we're calculating these forces. And so we're going to calculate F sub RY for this to determine those loads. So let's go back up to the top of the page. We're going to separate the roof and the ridge and some moments about the windward and leeward roof to wall intersection separately. The horizontal ridge force needs to counterbalance the applied wind load. So we're going to calculate that F sub RY and F sub RX. So we're going to come down here to the next table. We're summing moments. We're going to sum moments and come up with F sub RX of 336. In this case, I guess they end up being the same. Load 336 pounds per linear foot, and the maximum tension force F sub RY. Let me make sure I'm teaching you that correctly. Let me look here. Did I say we're calculating F sub RX? Yeah, we're calculating F sub RX, which is that horizontal load. Sorry about that, just making sure. And so that ends up being 336 pounds per linear foot when we sum moments about that location, and that's the value that's tabulated in what we just looked at. We talked about the footnote 1 and the reduction factor there of 0.7. So looking here in the bottom right of this page, when we look at the framing, the interior framing, and come up with that horizontal force rather than at the end zones of the roof, the ratio is actually 0.65. We rounded up, gave us a more conservative multiplier of 0.7 to cover all cases. So I think because this is at a very specific roof slope, if you were to check other roof slopes, you'd probably come up with some that might be closer to 0.7. So that 0.7 covers all cases that are tabulated there. All right, we'll keep on moving. We're about an hour in. We're going to take some time here in a second after this next poll to answer questions. I know we may be generating a lot of questions, so just hang in there. We're gonna take a little bit of a break here in a second to answer a few more questions. So this is table 2.2c, the rake, overhang, outlooker, uplift connection loads. Again, at 150 mile per hour, 24-inch on-center outlooker spacing, we have a value of 697 pounds for an uplift connection at that outlooker. So let me jump down here to the diagram so you can see what we're talking about. So this is the outlooker here on the left. I'll get that little red pointer tool spotlight. So here's our outlooker. You see it frames in across the end wall. And so then here is our uplift connector right here that we're going to size. So we want to make sure that we size this one appropriately to handle that uplift load. So we're going to have, you know, loads underneath this overhang and suction pressures and all kinds of stuff going on here. And so we want to make sure that we get that sized appropriately. First, let's make sure we take a look at the footnotes before we jump to the solution. Footnote 2, tabulated outlooker uplift connection loads are based on 2-foot overhangs. If the overhang is less than 2 feet, then there's an adjustment here, 2 plus the overhang length over 4 squared. So there's an adjustment for you if you're less than 2 feet. But notice over here for 170, 180, 195 mile per hour wind loads that we're gonna max out at 20 inches for the overhang length there. So that's what this footnote 4 is all about. That for those really high wind speeds and spacings, 20 inches is the max that we can do there. And that makes sense intuitively with those higher wind loads, right? All right, so jump to the commentary. 2.2c, rake overhang outlooker uplift connection loads. We're going to calculate those based on component and cladding pressure coefficients, assuming zone 3 and zone 3 overhang wind loads. So those are going to be those end zones, and we calculate a value for you for the interior zones. So here are assumptions that we just talked about. For zone 3 overhangs, here's our suction pressure, 78 pounds per square foot. That's huge. For zone 3 roof, it's 63 pounds per square foot. Also pretty substantial, but again, it's 150 mile per hour wind zone, so that kind of makes sense. So some moments about the first interior truss, and come up with an uplift load there of 349 pounds per foot, and at 24 inches on center, then that basically gets doubled to 697 pounds, and that's what's tabulated in table 2.2c. Again, if those loads are in zone 2 and not at the very edges of the roof, then you can calculate an adjustment factor of 0.6. I think we use a multiplier of 0.65. And footnote 4 then was where we show you the limit of 20 inches based on the bending capacity of that outlooker. So that, interestingly, doesn't have as much to do with the connections as it does with just the bending capacity of this outlooker under that kind of a wind load. So there's the calculations below for the bending moment on that outlooker, and we assume a fairly conservative design value. In this case, number 2, 2x4 Southern Pine outlooker, and calculate that capacity there. So that's what's going on with that additional limit that's in place there, that 20-inch limit. That is the length of the outlooker itself and the bending capacity of that outlooker. All right, so that gets us through to roof and wall sheathing suction loads. I keep looking for that poll question to jump up. It's going to be here in just a second, trust me. All right, so I highlighted a whole bunch of values here, and you'll see in a second that this is for roof and wall sheathing suction loads. Again, 150 miles per hour. Let's look at some of those zones that we've been talking about. So for a hip roof, we see the interior zone 1 and the exterior zone 2. The very corners are zone 3. Interior of the wall is zone 4, and the corners of the walls are zone 5. For a gable end application, pretty similar. Let's see what's different here. Obviously zone 2 is out here at the gable, zone 3 up here at the at the peak, the hip roof doesn't have this zone 3 up there where it attaches to the roof. It's only at the corners. So there's one difference there. So let's see. This dimension A is measured as 10% of the minimum building dimension, but not less than 3 feet. So there's an important footnote for how those zones are measured. All right, so how do we come up with those loads? This is the commentary then, believe. Yep, this is the commentary to table 2.4. Again, component and cladding pressure coefficients. The roof slope under background, the roof slope creating the greatest suction loads for slopes between 7 degrees and 45 degrees are tabulated. So over here, or let's look down here at the bottom, the maximum loads occur for effective wind areas of 10 square feet or less. The sheathing suction loads are therefore based on an effective wind area of 10 square feet for all roof and wall zones. And then we come over here to the right to calculate those roof pressures based on our pressure coefficients, our CNC pressure coefficients. So for zone 1, it's 25 pounds per square foot. Zone 2, 42 pounds per square foot. Zone 3, we just saw this one a second ago in one of our calculations, 63 pounds per square foot. The overhang at 78 pounds per square foot was another one that we just used most recently in that outlooker calculation. So those are the roof loads. Then the wall pressures, zone 4 at 27 pounds per square foot, zone 5 at 33.4 pounds per square foot. So there's that polling question. I'll stop there for a second, have Marcy come back and lead us in this next poll question.
All righty, here we go. So worst case MWFRS uplift loads occur at what roof slope? Is that 10 degrees, 20 degrees, 30 degrees, or 45 degrees? All right. I've got about 60% of you have voted, so the last 15% here quickly go ahead and let's see. All right, there we go. I'm going to close. And then it looks like 62% said 20 degrees, 18% 10, 11% 45, and 9% 30. So a little bit of a split, but the majority said 20%.
Okay, very good. More than half of you got the answer right. It is 20 degrees. And, you know, we do listen to input. We used to have very easy poll questions, and we got lots of comments saying, make the poll questions more difficult. So this one was covered a little bit earlier in the discussion, and we talked about main wind force resisting system uplift loads, and that the maximum occurs at 20 degrees. So I believe, Michelle, that's where we talked about stopping and doing some Q&A and see what kind of questions have rolled in with this first little more than half of our presentation.
That's right. And just administrative question that keeps coming in is I can't download the PDF. And one, the link is actually in the chat box, so if you open your chat box, there are links there that Brian has provided. Also, your web browser may be an issue, so we recommend using Google Chrome or Firefox, and that might help with downloading that PDF.
Yeah, okay. Maybe Brian, while we're doing some Q&A, you can post that link again and allow people to get to it. It's also on our resources page on our education, on the portal on our website. So.
Okay, so one question came in regarding page 10 of the PDF that you have. So if you can go to that.
Yeah, let me get my tools back here so I can go back up. And was it 10 of the PDF, like this overturning detail? Okay.
Yeah. So, a couple questions. One is that V at the bottom. Could you explain what that V represents? And so this is kind of a maybe 2 or 3-parter. The other is if you have shear walls, more than 4 shear walls in a line, can you explain how this works when you have more than 4 shear walls in a line, not just
Sure.
2 on each end?
Yeah. Okay, great question. So
there's a third part also. How does dead load play into this? For
okay, good questions. All good questions.
Okay.
So the lowercase v is the required unit shear capacity in pounds per linear foot of the panel. And so, and that's maybe what's causing some of the confusion here. Again, we in the wood frame construction manual assume that we're going to pick up 100% of the capacity of that panel to calculate that overturning load. And so we know that designers have different assumptions about that, and so that length L may be longer than what we're showing here in this calculation, but that's a simplifying assumption that we make in the wood frame construction manual. So if you have segmented shear walls, that's a little bit easier to see that, because each of those shear segments then is going to potentially pick up 100% of its capacity, and so then you'd need to size the hold downs around each one of those shear wall segments. But the reason we make this simplifying assumption is because when we go to the perforated shear wall method and we fully sheathe the entire building, it makes it much easier to size the perforated shear wall by assuming that that first panel picks up 100% of its load before it gets distributed on to the rest of the wall. That also sort of leads into the whole discussion about dead load. You know, if you've got a really short wall, a 10-foot wall, then, or an 8-foot wall, or a 12-foot wall, then yeah, tributary area on a 12-foot wall, 6 feet on either side, I could make a case for using dead load or 60% of the dead load to offset that. What if my wall's 40 feet long and it's a perforated shear wall, and now can I say 20 feet, half of that wall, 20 feet, is tributary to that hold down all the way out 20 feet away? And that's where it really gets tricky and requires a lot of engineering judgment. And so again, we make some of these simplifying assumptions, but still give the designer the clear permission in the document. It says that you can calculate these hold downs with perpendicular and resisting that load with dead loads, perpendicular walls, or mechanical anchorage. We don't use dead load to offset the hold downs in the wood frame construction manual. We use dead load to offset uplift. So that's the distinction that we make in the wood frame construction manual. Again, it makes it really easy, especially when you get longer walls, to not have to worry about how much wall do I have tributary to the end of that structure if I've got a perforated shear wall. So that's hopefully answers that question. Michelle, what do we have next?
A couple more. Regarding the snow load, it says 0 to 70 pounds per square foot, and there are tables based on 0 to 50 pounds per square foot, correct?
The tables go all the way up to 70, but we're going to talk about that next week. So
okay,
why don't we hold off on that one until next week?
Okay. Well, it was
or next month. Go ahead.
Okay.
Go ahead.
Well, someone said, well, can I design for 45 pounds per square foot snow load?
Let's tackle that one next week.
Okay.
We'll see what the footnotes say about interpolating.
Okay, and then one other question came in. When you were referring to ridge beam, are you referring to a ridge board or an actual ridge beam?
Good question. So that really depends on what we're dealing with here, and Oh, let me see, where did I talk about that?
It was just recently is what when their question came up.
Yeah. So let me try and answer it this way. For the uplift loads that are being carried by the ridge strap, it doesn't matter, because the uplift loads are going to occur whether it's a ridge beam or whether it's a ridge board. I think where the provisions kick in is at 3 and 12, a 3 and 12 pitch. I think anything less than 3 and 12 requires a ridge beam. And we'll have to check this and make sure that I'm telling everybody right, but I think there's a provision in the WFCM that mentions that. And so there are certain cases where a ridge beam is required, but those suction loads are going to occur whether it's a ridge beam or a ridge board. Now, there was a cutoff in that table at some point where once you get below 3 and 12, you really have a different kind of load. You really don't have much of a horizontal load anymore. It's more of an uplift load at that point. And so that's where the footnote kicks you out of that table into another table to calculate those loads. So hopefully we've dealt with that question as well.
Okay. So I don't think we have time for more questions, right?
Yeah, I think we do need to move along, because notice now we're more than halfway, and so we want to be able to cover some ground here.
Yep. Okay.
All right. Thanks for great questions, and hopefully we'll wrap up in time to take a few more at the end. Let me expand this so you can see. And we're in table 2.5a of the document. Lateral diaphragm loads from wind, and in this case perpendicular to the ridge. And so this is the in-plane shear and roof and floor diaphragm. So you see a diaphragm there of a 3-story structure. So we're going to be able to calculate these all the way up to 3 stories. This is impacted, since we're perpendicular to ridge, it's impacted by the roof pitch. So again, under 150 miles per hour and a 6 and 12 roof pitch and a 24-foot roof span, we come up with a unit lateral load of the roof diaphragm of 154 pounds per linear foot. So keep that one in mind as we jump down here to the bottom of the table, because some people miss this, and I think we need to move this to the top of the table in one of the next editions. This is the unit lateral load for floor diaphragms down here at the very bottom of the table. All right, so don't miss it. It's there, and that's 251 pounds per linear foot. So we'll talk about the tributary area and where that's all coming from here as we work through the solution. But again, this is perpendicular to the ridge. So the lateral loads are based on main wind force and are a function of the roof slope. And for the floor diaphragm, the coefficients are based on a worst case 20-degree roof slope. We do check those minimum 10 PSF and 5 PSF pressures that ASCE 7 requires. So that's all a sort of a lower limit. Let's see, scroll down here to the bottom, and we'll calculate the pressure. Pressure on the roof and walls is 21 pounds per square foot. I think that's from that one of the very first tables that we looked at. Again, this is around 150 miles per hour. And here are how we calculate the wall pressures then based on those windward and leeward coefficients. Sorry, I got to jump back up to the top of the page here. Since those pressures, I'm at the top right now, since those pressures act in the same direction, they'll sum to 20 PSF at the interior and 26.7, almost 27 PSF at the end zone. So again, we're assuming a box-like structure. If we assume that L is longer or shorter here in this next little exercise, it's going to give comparable results. But because of the way we set the diaphragm aspect ratios, it is a box-like structure. So this equation here that you're seeing, if you were to vary L and X, it's going to give you comparable results. And again, I looked at that pretty carefully as we were preparing for this. So we got that 24-foot roof span, a 6 and 12 roof slope, and so the pressures act in opposite directions, similar to what we talked about earlier. They sum to 7.4 pounds per square foot interior, 8.4 pounds per square foot at the end zone. So now we'll calculate an average pressure on the roof. So we calculate an average pressure on the wall, now an average pressure on the roof. And once we've got that, let's see, what was our wall pressure up here above? It was about 21 and a half, 22 pounds per square foot. Now our roof pressure is about 7.5 pounds per square foot. So the roof diaphragm takes the load from half the wall below and the roof diaphragm itself. And so we assume a certain top plate to ridge height, and obviously the wall height we talked about. So we tabulate 154 pounds per linear foot based on those coefficients and pressure, sorry. So now to calculate the pressure on the wall for our floor diaphragm, and for this we have about a 20 pound per square foot on the interior zone and a 30 pound per square foot load on the end zone. So that gives us an average pressure of about 23 pounds per square foot. Again, making certain assumptions about the wall heights, adding an extra foot to account for the depth of the floor joists, we come up with a load of 251 pounds per linear foot. And then in the footnotes, I believe we allow for adjustments for other than 10-foot wall heights and adjustments for other than the 10-foot top plate to ridge height. So further on in the document, I think in Chapter 3, you get those allowances. So then parallel to ridge is going to be a little bit different, obviously, based on the wind loads, but we still do have a roof pitch assumption here. So we're going to base it on a 7 and 12 roof pitch and 24-foot building roof span. So that is 132 pounds per linear foot. Going that direction, and for the floor down here at the bottom, 171 pounds per linear foot. So don't miss, again, at the bottom of the page, the unit lateral loads for the floor diaphragm. All right, so then back to the commentary, table 2.5b, again, main wind force loads. This time it includes the contribution from the triangular portion of the gable end wall in addition to the tributary portion of the wall below. So let's see if there's a picture of that somewhere. I thought I had a picture. Maybe we'll see it show up here in a second. But it is the contribution from the triangular portion of the gable end wall, again, in addition to the portion of the wall below. So we've got a 7 and 12 roof pitch, and that's for calculating the tributary area of the entire triangular gable end. Okay, so it's a little hard to see the note that's popping up there, but that 7 and 12 roof pitch is to allow us to calculate this little triangular sail here in the air. Obviously that's, you know, not drawn to scale. That's not a 7 and 12 pitch. That's a pretty low pitch, but you get a big 7 and 12 pitch, and it's going to, you know, really give you a large gable roof load there. So that's why parallel. We're even including the roof slope in this parallel to ridge wind load. So we've done. I'll get through this pretty quickly because we've done this exercise earlier. We're going to calculate an average pressure on the gable end wall. Came up with about 15.5 pounds per square foot. Calculate lateral load on the roof diaphragm. That ends up being 132 pounds per linear foot based on that average pressure on the gable end wall. All right, so the note here says that the calculation for the roof assumes there is no attic floor ceiling diaphragm. If there is an attic floor ceiling diaphragm, you can, the lateral load can be used or can be reduced by subtracting what goes into that attic floor ceiling diaphragm, and we're going to look at that one next, I think. So similar calculation for the floor diaphragm to what we saw earlier, so we won't spend any time going through that. Here we go. These are the notes I was looking for. So footnotes to table 2.5a and b. Footnote 2 is one of the ones that I was mentioned just in passing. The unit lateral loads are based on a 10-foot wall height and a 1-foot floor depth. For other wall heights, you can multiply by h plus 1 over 11. So that allows you to account for a different wall height. We've talked about these other footnotes. Footnote 4, though, I'll point out that the hip roof system is designed using table 2.5a for both orthogonal directions. And if you remember, we looked at that hip roof earlier and the loads there. You obviously don't have a gable end load on a hip roof. And so you can use 2.5a for both directions with a hip roof system. So the shear capacity requirements are just spelled out here in footnote 5 to give you a sense of load path and what needs to be considered in the design process. All right, here's that attic floor ceiling diaphragm for bracing a gable end. Now the difference here, I want you to look carefully at this tributary area. What we calculated earlier for roof diaphragm load included the entire gable end. In this case, we're going to calculate the load on this roof, on this attic floor ceiling diaphragm here shown on the left. So let me get my little pointer tool to make sure you're seeing what I'm talking about. But that's the attic floor ceiling diaphragm there on the left. And this gable end, the shaded region, shows that we're only accounting for half of that triangular gable right there into that. The rest of it's going up into the roof diaphragm itself. So this is one of the assumptions you need to be aware of as we look at this table. Again, we're typically looking at an example using 150 mile per hour wind speed and a 6 and 12 roof pitch, a 24-foot roof span. So we're looking for a value of 101 pounds per linear foot on that diaphragm. I put the footnotes here ahead of the commentary in this case. So again, we're based on 10-foot wall heights. It looks like we don't give an option there to reduce that one for whatever reason. Footnote 3 is pretty important here as well. So the attic floor ceiling diaphragm is assumed to be continuous between end walls. If the diaphragm only resists loads from one end wall, then it shall be multiplied by 0.84. And where would something like that occur? Well, if you've been with us in some of our other webinars, you know we've done an example where we've got a vaulted ceiling over top of an upper story bedroom, and then on the other end of the house you might have a finished attic space. And so if, in that case, the floor ceiling diaphragm, the attic floor, doesn't go from end to end of the structure. And so there's a case where your floor ceiling, attic floor ceiling diaphragm is not continuous across the length of the building. Footnote 7 says when a ceiling diaphragm is used to brace the gable end wall, the unit lateral load on the roof diaphragm need not exceed the tabulated roof lateral load from 2.5B minus the ceiling lateral load. So this is just giving you a sense of, if you're calculating these using these ceiling diaphragm and then calculating roof diaphragm loads, you can deduct what you're calculating here for this attic floor ceiling diaphragm from your roof diaphragm loads. So that makes sense if you're gonna take that approach. So here's the commentary for this. Again, we're parallel to ridge. We've got that tributary area gable plus half the wall below. Main wind force loads. Lateral forces into the attic include the tributary from the triangular portion of the gable end wall and the wall below. I just stated that. We calculate a wall pressure of 15.5 pounds from table 2.5B, which is an earlier table that we looked at, right? So we've already got that wall pressure. So then, sorry to be jumping around here, I'm trying to get to the calculation. So here we've got half the gable and then half the wall for a total square footage of 156 square feet. And that, once you using the wall pressure that we just calculated, gives us 101 pounds per linear foot, which came out of the table. Okay, read this under footnote 3. Says for a gable end wall, the worst case main wind force load occurs on the windward wall. Tabulated loads may be conservatively reduced by taking the ratio of the windward load for a single end wall to the windward and leeward wall load. So that's what's happening with that footnote that says that you can reduce or use that factor of 0.84 is because you if it's not continuous across the full length of the building, you won't have both a windward and a leeward load on that attic floor ceiling diaphragm. Again, that makes sense, and that's what gives us this reduction factor here of 0.84, which is what shows up in that footnote. And then footnote 7. So if we were to look at the example we calculated earlier, I think it came up with a value of 124 pounds per linear foot, and we deduct this load that we calculated for the attic floor ceiling diaphragm, we see that the lateral load on the roof diaphragm can be reduced down to 23 pounds per linear foot. So, all right, I'm going to keep rolling here. Marcy, I'm going to skip past this poll question. Sorry, we're
no problem.
A little short on time, so I want to make sure that we cover the rest of the material that we want to cover today. So
perfect.
This one's important too. It's the exterior wall stud bending stress from wind loads. So here I've only excerpted half the table. This one actually spreads across 2 pages. So the 150 mile per hour wind speed is over here on page 81. Page 80 has the other lower wind speeds. So for a 10-foot wall height and a 16-inch on center spacing, we come up with an induced bending load, F sub B, bending stress of 1,820 psi. So we've got all the footnotes that we've seen earlier, except number 3 says the bending stress shall be less than or equal to the allowable bending design value. So if you're using these to calculate that bending stress, then you just have to calculate a bending value per the NDS to come up with your solution. But let's talk a little bit about computing wind pressures using CNC coefficients. And this one is something we need to spend a little bit of time talking about. So the peak suction forces are high, And so we're looking here at the background. So defining the effective wind area and the tributary area of the wall stud is a key to obviously computing suction. So the stud span equals the wall height minus the thickness of the top and bottom plates. So we go through that calculation. For CNC wind pressures, okay, this is where you need to pay attention. For CNC wind pressures, the bending stresses are computed independent of axial stresses. In addition, the bending stresses for main wind force pressures act in combination with axial stresses from wind and gravity, and those must be analyzed. But for the buildings limited to the conditions in this manual, CNC loads control. So let me just state this a different way. When we do a stud design in the wood frame construction manual, we're only looking at the CNC wind load alone. When we look at a combination of combined bending and axial, we use main wind force loads for that. And those don't control because the CNC loads are so much higher. So that's how we do stud design. And if you're trying to do a combined bending and axial load using CNC pressures, you can't get it to work. It just because the loads, the CNC loads are crazy high. So Brian in a second is going to be posting this link to this document. It's called Considerations in Wind Design of Wood Structures. I don't have time to go through all the details here, but you can download this document, and if you won't take my word for it or take what we said here in the commentary at face value, you can run through the example yourself to see that what the backup for the assumption that we're making in this document. So that makes the calculations very easy. CNC loads on a stud gives us a bending moment of 464 foot-pounds. We crank that through an MWFRS equation to calculate our bending stress of 1,820 psi, which is what we tabulate. So again, download that paper if you want more background. That then leads to this induced moment table, which we pretty much just talked about. So you can either calculate an induced moment or a bending stress if it's a stud. I guess if you were using a hoist or a truss or something else in a wall and you wanted to just calculate the induced moment, this table would allow you to do that. So I'm not going to take a lot of time to go through. It's a really simple calculation once you know what the assumptions are for using CNC wind pressures for that. So we'll jump on past that and then go to our last polling question before we hit our last few slides. Marcy?
Terrific. All right. So for calculating exterior wall stud stresses per the WFCM, which of the following is true? Buddy, actually, now that I've done this, we were going to leave the your slide up so they could read it.
Why don't you go ahead and read it
okay.
from my slide. And just they're already taking the quiz, so let them keep going.
Okay, so for CNC, bending is computed independent of axial loads. MWFRS bending combined with axial loads must be analyzed. For WFCM design buildings, CNC loads control studs or all of the above. So I apologize for the abbreviated answers, but you all are very on top of the game and know your stuff. So for calculating exterior wall stud stresses per the WFCM, which of the following is true? All right, so we've got about 60% of you have voted. And most of you have voted one way, so I'm going to go ahead and I think close it. So let's go ahead and share. I've got 69% said all of the above, 14% D, 9% A, and 7% B. And Buddy, the real answer is?
The real answer is all of the above. 69% of you got that right, and that's again the concept we were just talking about. We're going to do CNC bending alone, independent of the axial stresses first. Then we're going to do main wind force bending and axial stresses, and we're going to compare those two. And for the buildings inside the scope of the wood frame construction manual, those CNC loads control. So all of the above are true in this particular slide. So that's something we want to make sure that you get. And this poll was there were a lot of words that we were trying to cram in here, and unfortunately the polling software with GoToWebinar doesn't allow for that many words. So you all figured it out, so great job there. Okay, so this last one that we'll look at, and then it looks like we're going to have some time for some Q&A here at the end, has to do with rafter spans. And so you may be asking yourself, well, you said we were going to do the gravity loads next month. Why are we talking about rafter spans? Well, there are uplift loads on the rafters that we need to consider. And so I want to just introduce this commentary section and look at one of the footnotes here that we'll be talking about this week and next week. So first thing is at the top of the page, we're looking at a 20 pound per square foot live load table. Okay, so that's important. We're not gonna look at the ground snow load tables this week. We're going to look at the live load table. And then we've got different dead loads here across the top, 10 and 20 pounds per square foot, and we've got some different deflection ratios depending on whether you've got brittle or flexible or no ceiling attached. And then we also tabulate spans for 2x4s all the way up to 2x12 rafters. So this is a maximum horizontally projected span. Again, we'll talk about some of the gravity stuff a little more next week, but if we go through a gravity design, and this example, assuming we have a bending value of 1,600 pounds per square inch, and we're at 16 inches on center, we tabulate the required E value for stiffness, and then we also tabulate the allowable span, assuming that strength calculation there. So that's an 18-foot 9 span that would be allowed for a 20 pound per square foot gravity load. Okay, so that makes sense. A pretty small load, and that's a 2x8. So 2x8 spans almost 19 feet with a 20 pound per square foot roof live load. All right, so let's take a look at the footnotes. I'm going to skip footnote 1 and 2 because we're going to pick that up next month, and I'm going to jump right to footnote 3, bottom of the page here. So what we do here is that we provide a table for both exposures B and C to determine the maximum rafter span for wind loading. So you're going to multiply what you just determined from 214A by the adjustment factor here in this table to get your allowable span for 150 mile per hour wind load, and this is a suction load on the rafter. So we've got it tabulated for the end zones, 4-foot end zones, the interior zones up to 6 and 12. Okay, so that, note carefully the zones up to 6 and 12, interior and end zones, and then for 7 and 12 to 12 and 12, we don't have to separate the two. It's just it's going to be the same factor for those higher pitches. So that's, again, we've gone through ASCE 7 and looked at all those coefficients, so this kind of simplifies that process for you. So we'll show you where we come up with a 0.73 factor, a 0.91 factor, and a 0.84 factor. And here's the commentary. So we're going to perform calculations for E and FB and adjust for wind uplift in this case under the procedure. So we're assuming a simply supported beam, and again the horizontal projection of the rafter. Again, next week we'll talk probably a little bit more about what's bulleted here, about a more sophisticated approach, but this kind of gives the background for why we assume a horizontal projection. So I'm not going to spend a lot of time, again, going through the gravity analysis. It's a pretty straightforward analysis to come up with that 18'9" span that we have in the table. So you can look at that on your own. I want to jump right to the wind load analysis here in footnote 3. So what we're doing is, again, we're looking at the uplift on the rafter, and we're going to calculate the bending capacity of this rafter based on that wind load. Okay, so we're going to take a look at the 150 mile per hour, exposure B, in all these zones, use component and cladding wind exposure coefficients. We've shown you where we're taking that from ASCE 7 down here to come up with the wind pressures. So then back to the top of the page, you see when we determine our net uplift, top right, 90 pounds per linear foot net uplift for 150 mile per hour wind load. So we take that, we plug it into the bending equation, and we're going to take a ratio of the load duration factors to account for the difference in the roof, live, and wind load. So that's what shows up down here, the 1.6 over 1.25 ratios out that load duration factor to come up with an allowable span for that wind load of 14 feet. All right, so we take a ratio of that to what was allowed back in the table, and we take that ratio, 14 to 19.5, and come up with 0.72. So that, I think we list a multiplier of 0.73. But that is just some rounding differences that are involved. So that also gives you a quick way, I'm not going to say quick and dirty because it's a detailed analysis. It's a very quick way to calculate wind uplift on your rafters using a simple table, a simple set of lookup tables, and compare that to your gravity loads. Obviously, if you've got ground snow loads, 30, 50, 70-pound ground snow loads, most of the time that's going to control. But if you're in those high wind regions along the Gulf Coast where you don't have a lot of snow, this could very well control the design of your rafters. So I'm not going to go through the other zones there. The analysis is very similar. I've highlighted that and how we came up with those other coefficients, 0.9 for that interior zone, and then 0.84 for the slopes greater than 7 and 12. So you can look through that on your own. And we're getting here to the end of the program, and I think we've got about 5 to 8 minutes left for some Q&A. So I'll ask Lori and Michelle, if you would, to come back, and let's see what kind of.
Okay, there's a few questions that came in. One comment is having to do with the wood frame construction manual being a valuable resource, and then possibly more education on utilizing this, because some people could see it could be a full workshop. Are there ever any workshops, you know, rather than 2-hour webinars like this?
Yeah, great question. I'm actually going to pull up the website here and give a little plug to our education page. I'm going to jump to the education page. I'm going to go to our e-courses page first and talk about one of the webinars that we've done in the past. It is a full-day workshop. We've condensed it down here. Let me get to the right section, bottom of the page. This was one we did a little bit earlier in the year, STD 335, Disaster Resistant Wood Frame Construction, Part 1, Loads and Roof Story Design, where we actually go through and design a 2-story structure for both high wind and seismic loads. And so that webinar is actually recorded and available here on the website. You can go to YouTube and download it. You can download the workbook itself at any point if you want to. Let me pull that up real quick just so you can see what that looks like. And here's a quick snapshot to get there of the building, what it looks like, the floor plan, two-story building with some windows in it. And then the floor plan shown here. So we designed that entire two-story structure for high wind and high seismic loads. So good question.
Another question came in. Will we have a live webinar similar to this for seismic loading?
So good question. There are only a handful of seismic tables. If we do that, we'll probably do it sometime next year, and I'm guessing that might only be a 1-hour webinar. As it turns out, there aren't as many seismic tables, primarily for shear wall design, but we do have that on our radar. We wanted to tackle these two for wind loads and gravity loads next month, and then probably build that into our schedule sometime in 2017.
Okay. Another quick question having to do with the bearing walls and compression perpendicular to grain on the plates. How does that you accommodate for that, checking that?
Okay, so that is a good question, and one of the limits that we have in the wood frame construction manual is a limit on the span of the rafters and trusses and joists, and we don't show it here on this page, but we do limit rafter spans to 26 feet, and believe and floor joists the same. I believe we have truss and I-joist limits of either something comparable to that or a little bit higher, assuming that they will have some interior bearings. But there are a couple of things that we check in the load path to limit those spans. One is the bearing of the studs, which can impact the capacity of the walls. The other, though, is the bending of the double top plate. So if we've got studs, for example, at 16 inches on center, and then rafters or trusses at 24 inches on center, invariably you'll have a rafter or truss land right in the middle between two studs on a top plate. So we looked at the bending capacity of a double top plate, and that ends up limiting the spans of the rafters and joists because of the bending of that top plate. And there are other limits as well for headers. We calculate jack studs based on bearing capacities. So yeah, that's all accounted for, and we'll talk about more of that next week in the gravity section.
That's great. A lot of forethought into all of this.
Yep.
So do we have time for one more question?
One more. Yep.
For those rafters that were being checked for uplift, wind uplift, what about, how does it accommodate for the bracing of the compression part of the rafter? Because you made it.
Yes. So when we go back, in fact, I'm going to go back down there just so you can see it. It was just a real simple bending calculation when we went through the analysis. So I'm going to get there. So F sub B WL squared over 8. And then then we just do an FB over S, and we don't have to worry about the C sub L factor for beams because we've got sheathing across the top of those rafters, so that braces it in compression. So great question.